Hello, everyone, and thanks for joining today's webinar. My name is Amy Bowie-Perez with Mphasis Stelligent, and I will be your webinar host today. Before we dive into the presentation, I'd like to cover a little bit of housekeeping. This webinar is being recorded, and an on-demand link will be available and shared with you post-webinar. Please feel free to share the link with your colleagues. You can submit any questions you may have in the Q&A box in the lower right-hand corner. We will spend some time at the end of the webinar today to answer your questions. If we do not get to your questions during the webinar today, we are happy to follow up via email. And last but not least, if you are on Twitter or LinkedIn, be sure to follow Stelligent for news, resources, and announcements for future webinars. Today, joining us, we have Dante Martinez, Senior Solutions Architect. Dante is an AWS certified solutions architect with more than 20 years of experience building software delivery and operation systems. He brings a true mastery of the DevOps and SRE frameworks, resulting in solutions that lead product, development, and operations teams to the highest success levels. Dante is part of an all-star team that architects and develops solutions to accelerate, secure, and modernize software delivery and operations. Also joining us is Rajesh Matkar. Rajesh is a principal solutions architect database at AWS. He has been with AWS for the past 4 years, focusing on Amazon Aurora and other relational database solutions, educating best practices, and helping customers and partners modernize their database platforms. Rajesh has over 25 years of experience in relational and non-relational database management, and he also has 2 master's degrees, one in computer management and the second in commerce. At this time, I'd like to pass the mic over to Dante and Rajesh.
Yeah, thanks, Amy. So I wanted to give a quick introduction to Mphasis Stelligent. So Mphasis Stelligent was founded as Stelligent back in 2007 and has been an AWS partner since 2009. So we've been working pretty closely with AWS almost since the beginning days. And we've developed some really key relationships there. So every one of our employees is AWS certified. That includes even our administrative and back office people, so not just our engineers. So we really do live and breathe AWS day to day. And our mission is simply to help organizations accelerate, secure, and modernize their software delivery. And we believe strongly that AWS is the platform of choice to do that. So we're a premier consulting partner. We've got competencies particularly in DevOps and security, and we've got a couple of vertical competencies in financial services, travel and hospitality, and the public sector as well. And our focus is typically on DevOps, security compliance, and now DataOps as well. So our general philosophy, right, is development through automation. And our goal for anyone is that someone can have an idea in the morning, so a new feature, a new bug fix, whatever it is to improve your software or applications. And we want you to be able to deploy that with confidence on the same day, right? So we do that by using the DevOps and DataOps methodologies. And key to that is to speed up the feedback loop. So through automation, we can do things like check for quality of your code, check for security of your code, and check that things are set to your enterprise standards and give you very fast feedback on that. So your developers can increase experimentation, gain confidence, and reduce risk and get that software out as fast as possible. So with that quick introduction, I will hand it over to Rajesh, and he's going to talk to you a little bit about the modern data architecture on AWS.
Thank you, Dante, and good day, everyone. So yes, as Amy mentioned, I have been helping AWS customers and partners more than 4 years. Let's see how the modern data architecture looks like. Today, we will focusing on data side of the equation, and in particular, we will take a look at how automation in the form of DataOps is an enabler of cloud-based modern data architectures. But first, let's make a movement to contrast a modern approach to a classic, but still common architecture. So this is a bit simplistic, but we are simply showing how in a classic data architecture, your focus is on monolithic database or store. In this example, we have got 4 applications: order, inventory, pricing, and shipping services that all interact with a single shared database. Then you have also got a single shared analytics database. In between, we have a limited set of pipe to move and prepare the data for analytics. Now, this setup works fine, just fine. In fact, millions of companies are still running on the design like this. It can be difficult to make the decision to move away from this type of the architecture when you have invested a great amount of time and money building out the infrastructure and developing ETL processes, stored procedures, analytics, all based on the single source of data. So what I see a lot of companies do first is they look for a cloud equivalent to replace their single monolithic database. This can definitely be done, but it's often disappointing because you end up with the same problems related to use of the monolithic architecture. Just as with the monolithic applications, the biggest drawback is that you create a tight coupling between your database and every application's service, ETL process, or report that interact with the single data set. This means that any changes to that data set or infrastructure running that database, you must coordinate with everyone involved. This slows production down as you must know that test your change against dozens or hundreds of the database is potentially a single point of failure, which is also a single source of truth. Each service has a different kind of a data requirement, and data model is always different. The next drawback is that scaling and the performance becomes incredibly difficult as your data sets grow large. The cloud has made resource scaling trivial, but still challenging to scale ever-growing monolithic data sets. Improving application performance becomes difficult. Imagine, if you will, a single shared database, which over the time end up with the rather large tables. This can make a make a data retrieval difficult since you must join multiple large tables to fetch the required data. Data volume has been increased and now measured in terabytes and petabytes. Speaking of constraints, you are most likely stuck with using a single relational database for your monolithic, meaning that your all applications are constrained to also using the same relational database. This leaves you unable to take advantage of NoSQL or other lighter weight options for your applications and services. Lastly, the monolithic database makes finding and accessing data difficult as it grows. We have all been asked, where is my data? Which usually kicks off a time-consuming process to finding specific data sets, describing the use, and making them accessible for consumers. All of these problems are add up assembly line bogging down in terms of data development and consumptions. So there is one thing I want to take away from this brief comparison, that there is a price to pay in staying on this type of the architecture. In terms of long, slow development cycles, which equate a long, slow, and expensive business decision cycles, while your competition leaves you behind. Okay, so what's an alternative approach? Again, this is a bit simplistic, but we are showing here what those same 4 applications might look like in a modern data architecture. Here you see each application or service has its own database or store and use different database technology. A relational database like Amazon Aurora might be best option for pricing service, but not ideal for inventory and shipping services, and vice versa. With a modern microservice architecture, you can choose the best database for the job, such as a NoSQL database like DynamoDB or a graph database like Amazon Neptune, that is the right tool for the right job. Each applications own its data set independently of each other, meaning you can make changes to that data set without concern of disturbing another application. You are now free to deploy any given service and data sets or changes to those independently of your other services. This also means you can scale easily by simplifying scaling these smaller discrete databases or store on demand. Good performance from the application standpoint, it's also easier to achieve as you no longer must deal with joining and moving large sets of data that are irrelevant to any particular application. Now, another way to visualize this is to see that your application and data set stacks map to your business domains and have you bounded constructs based on business requirements. This is a code first versus a data first approach, where your business requirements drive the code design first, and then functional code drives your database design. Now, with the newest things about the surfaces, when that consumer comes asking once again, where is my data? Now, instead of a arduous search followed by an urgent operation to make it available, I can simply point them to a directory of datasets, each of which is discrete and self-describing and was defined by a business domain. In fact, done properly, you will never hear this question again because those business domain stakeholders would have been involved in defining and deploying those datasets from the day one. Now, two key principles of designing a modern data structure. Database or data stores are discrete and belongs to their assigned application or microservice. They are private. So the inventory service cannot access or modify data in the shipping service and vice versa. This great things about this is what, if you want to make a change to my inventory service, I don't need to involve my shipping service team to do that. I am free to innovate and iterate on this service as business requirements demand. I can scale my inventory service database on demand without worrying about the state of my shipping service. Providing access, securing, and monitoring my inventory data set is also greatly simplified because only the inventory service needs access. Now, our applications and services do need to interact. Still, we do this utilizing an event-driven architecture. In this model, you provide loose coupling between applications and datasets by utilizing message queues and pub/sub event-driven data flow. Instead of waiting on a resource-intense ACID transaction, you can make your application more available and performant by offloading events to a queue via message. Your application can define and self-describe these events in publishes independently of the subscribers. In fact, your application won't even be aware of the subscriber or what they do for those messages. It's this loose coupling between components of your architecture that enable you to build highly scalable and distributed system. Now, you are used to thinking of pub/sub model in terms of applications, but there is no requirement of an application or service to be involved. Most cloud native database or data stores have an ability to send messages based on the data events. This means that you can trigger actions based on data lifecycle events, allowing you to orchestrate data flow independently of the applications as well. Okay, so a quick overview of few other characteristics of modern data architecture. First, it's very adaptable. In a modern data architecture, data flows like a water from source systems to business users. The purpose of this architecture is to now orchestrate that flow by creating a series of interconnected data pipelines that serve business needs. The pipelines are constructed using base data objects, data snapshots, data increments, data views, references, data primary data, and the flight subject-oriented tables. The data objects serve as the building blocks that are continuously reused, repurposed, and replenished to ensure the steady flow of high quality and relevant data to the business. Next, it's a collaborative endeavor. Unlike the past, where the IT departments built everything, and a modern data architecture share responsibility of acquiring and transforming data between IT and the business. Data engineers and analysts in a business units use data preparation and data catalog tools to create custom data sets composed of corporate and local data and provide them for the use of business applications. Modern data architecture is also smart. This goes beyond the automation and includes the use of machine learning and artificial intelligence to build the data objects, tables, views, and models that keep data flowing. It uses intelligence rather than the brute force to identify data types, common keys, and joint paths, identifying and fix the data quality errors, map tables, undefined relationships, and recommended related data sets and analytics. A modern data architecture uses intelligence to learn, adjust, alert, and recommend, mapping people who administer and use the environment more efficient and effectively. Finally, a modern data architecture that governance and security into the data sets, workflows, and pipelines. It does by making each component responsible for its own security and governance. A data set subdescribed by means of metadata who has access under what condition a form of data can be shared. A pipeline must respect those conditions as it moves data from one location to another. So for example, a data set that originated in EU might be tagged as a GDPR compliant, and a pipeline would be prohibited from moving data outside of the EU. A data set that originated with the private medical information is tagged as a HIPAA compliant and does not provide access to applications and users outside of the defined consent boundary. Additionally, each dataset is tagged and self-described as its lifecycle information. Each object has an owner, location, and obsolescence plan, for example. Okay, so we have got an idea what modern data architecture looks like now. Now, there is always catch, right? And this where we start to see the requirements for automation and a DataOps framework in order to successfully build and operate a modern data architecture.
Yeah, so thanks, Rajesh, for the overview of the modern data architecture. And it's certainly the path we see a lot of organizations take as they modernize their applications. So I'd like to talk a little now about why the DataOps framework is a necessary requirement to implement a modern data architecture. So with any distributed architecture, the primary trade-off is that you now have many more objects to manage independently. In terms of provisioning for each application, you may now have dozens or potentially hundreds of independent database stores or objects. And each of these objects has a life cycle that has to be managed. And each of these objects must be provisioned, configured, operated, and monitored as well. And what's more, you must now orchestrate a large number of data streams and movements. So in the classic architecture, this was limited to a handful of movements from large database to another large database. Now each and every data set may interact with every other data set, leading to an exponential increase in the paths that your data may travel through your application. And also, all of those nodes that you've now deployed also need to be secured and governed. So more endpoints equals more ways to infiltrate, and you need to define and manage access, use, network, and store controls for many more objects now. And you must monitor for secure interactions on a much larger set of data flows. Finally, all of these areas, provisioning, orchestration, and security, are defined in code. Infrastructure is defined in code. Your pipelines to deploy that infrastructure are defined in code. The data sets that are now self-describing all come with metadata, which is code. The pipelines and step functions that define the movement of data are defined in code. Data operations like ETL, conditioning, preparation, all that's defined in code now. Security, use, and access, all metadata code attached to the data sets. And the orchestration of everything I've talked about, all of this is defined in code now. So code is everywhere now, and you must now manage the creation and iteration of that code as well. All of these new management requirements can sound overwhelming at first, but with the right approach, this overhead can be automated and operations can be efficiently conducted. So that's the goal of the DataOps framework. All right, so let's start with a textbook definition so we can get that out of the way. The DataOps framework is a set of technologies and practices for building, operating, and managing data pipelines from source to consumption. So DataOps is a subset of the DevOps movement in the software engineering world. DevOps bridges the traditional gap between software development, QA, and operations, so technical teams can repeatedly deliver high-quality systems at an ever-increasing pace with no loss of stability or governance. Like DevOps, DataOps shares responsibility for operation with all stakeholders, which on the data side of the coin means data architects, data engineers, data scientists, data analysts, application developers, and IT operations collaborate to deliver on the organization's need for data. DataOps borrows heavily from Agile, Lean, DevOps, and total quality management from the manufacturing world. And similar to Agile, DataOps emphasizes the use of small development teams with business involvement and short, typically 2 to 3 week development sprints that deliver fully tested, production-ready components and code. Similar to Lean, DataOps focuses on efficiency using version control systems and code repositories that foster parallel development and code reuse. And like total quality management, DataOps focuses on continuous automated testing and monitoring to detect issues before or immediately upon promotion to production. Now, from a business point of view, DataOps takes in business requirements for data on the left and outputs business value in the form of data that can be used for guidance for your business decisions. Now we'll look at the framework from the data lifecycle point of view. From this perspective, DataOps takes in raw data sources on the left and outputs refined data ready for consumption on the right. The processes involved in the lifecycle are defined by business domains, codified, and then implemented by operations teams. Each of the steps you see here in the data lifecycle has tooling and automation that can be leveraged to reduce the overhead and management time required. This in turn improves the cycle time to value of your data. Okay, so what does it take to implement the DataOps framework? We'll now take a look at the 4 epics to build out and apply the DataOps framework inside of your organization. Okay, so epic 1, as I mentioned before, everything is code now. To extract value from data, you progress through a series of steps. So data needs to be conditioned, validated, transformed, combined, modeled, moved, analyzed, and reported on. And conceptually, the pipelines used for these stages are implemented using a variety of data tooling, including ETL, data science tools, self-service data prep tools, reporting tools, visualization tools, and more. These stages are then executed by a pipeline in a deterministic fashion defined by scripts, source code, algorithms, config files, parameter files, and containers. And each of those items exists as a set of code. So code controls the entire data pipeline from end to end in a reproducible fashion. And the artifacts that make this reproducibility possible are also subject to continuous improvement. So just like other software projects, the source files associated with the data pipeline should be maintained in a version control system such as Git. A version control tool helps teams organize and manage the changes and revisions to code. and it also keeps code in a known repository and facilitates disaster recovery. However, the most important benefit of a version control relates to a process change that it facilitates. It allows data team members to branch and merge. So in a typical software project, developers are continuously updating various source code files. And if a developer wants to work on a feature, he or she pulls a copy of a relevant code from the version control tool and starts to develop changes on a discrete copy called a branch. This approach can help data teams now manage changes to the data pipeline in parallel. When the changes to a branch are complete and tested, the code from the branch is merged back into the trunk where the code came from. Branching and merging can be a major productivity boost for data teams because it allows teams to make changes to the same source code files in parallel without slowing each other down. Each individual team member has control of his or her work environment, and they can run their own tests and make changes, take risks, and experiment independently. If they wish, they can discard their changes and start completely over. This leads us to the next capability you will need to build for a DataOps implementation. Allowing team members to work well in parallel relates to providing them with an isolated environment where they can deploy their branches. So in Epic 2, building on the DataOps framework, you see each data team member has their own development tools in their own work environment. Version control allows team members to work on their own private copy of the source code while still staying coordinated with the rest of the team. For most data development, a team member can't be productive unless they also have a copy of the data, or at the very least a subset or representative set of that data. If everyone tried to work from a single source, conflicts would occur. A database engineer changing a schema might break reports. A data scientist developing a new model might get confused as new data flows in. So providing discrete environments to each team member isolates the rest of the organization from being impacted by their work. Here we see how version control, branching and merging, and multiple discrete environments work together. So note that each environment was provisioned from the same configuration template. So at startup, they are identical. Each, however, will execute a different branch or version of the code. And this allows you to isolate environmental factors from issues with your executing code. Now, on the data development side, the environment consists of a defined data set and the operational resource that runs your application, transform, model, or other service that interacts with the data set. Ideally, this operational resource is in the form of a containerized package of code. And once that code is placed in a container, it is much easier to use by other programmers who may not be familiar with the custom tools inside the container, but know how to use the container's external interfaces. It also simplifies deployment of that code to each environment. Now, in most cases, your workflows are going to need the capability to incorporate different runtime conditions as well. Which version of a raw data set should be used, for example? Is this data directed to a particular environment? Or should a particular filter, say a PII filter, be applied to the data on ingestion? Or should a particular set of processing steps in the pipeline be applied or not? A good pipeline design will allow the engineer to invoke these options by utilizing parameters instead of writing a new workflow out. A parameter is simply a flat flag passed to the pipeline that affects the way it operates. So imagine, if you will, an engineer has just created a new data model and would like to test it independently with data sets from two different regions. In this case, the engineer can simply pass the America parameter to load the data set from the Americas in this first run. And on the second run, they can pass the Europe parameter to the same pipeline and load the data set from Europe. This ability to pass parameters into your pipeline allows your engineers to work in defined environments, but still maintain flexibility to develop and test with different runtime conditions. Okay, so what does provisioning an environment look like? Here we can see an example of an analytics environment with three components defined: an input data source, a data transform, and the analytics code itself to generate reports or other refined data. All of this is declared in code, in this case in the form of a YAML template. And the engineer created this template and the pipeline provisions that required infrastructure and configuration based on that template. But now we can also iterate on this as needed. Let's say we need to add a new data source. The engineer can simply modify the template to add the new data source. And the pipeline then provisions the environment into a temporary testing area, executes a series of validation checks, and then, assuming everything checks out okay, provisions the environment into a work state area. Okay, one last takeaway on environments. Those templates that define the environment are immutable. That is, each and every time the pipeline reads a specific template, it will provision the exact same environment. It doesn't matter if that environment will be used for testing a new feature, fixing a bug, or to deploy your final production code. The environment will operate exactly the same in each use. This allows you to independently test your code without worrying about issues with environmental runtime conditions. All right, so we'll take a bit of a tangent on our DataOps journey, but security is often defined together with the environment itself. So in the DataOps framework, security definitions are baked into each data object, and the pipeline is the application and enforcement mechanism for those controls. A layered set of controls is used to ensure that requirements are met. The first of the layers is a preventative control used typically to validate a data object or resources configured correctly before deployment. And the next layer will utilize the same control definition, but will monitor for violations after deployment in the operational environment, and also continuously in any running environments. This is known as a detective control, and it will flag and notify of any runtime violations. And the last layer, a reactive control or remediation control, will take any output from the detective control and trigger an event that can remediate or take further actions to mitigate or correct the violation. All right, so let's take a closer look at how these controls work in the context of a DataOps pipeline. Here we have an example of a preventative control. Our engineer has attempted to deploy a data store without encryption, and the pipeline will execute a static analysis of the configuration template, and upon seeing the violation of that requirement for encryption, it stops before deployment and can generate an error for the engineer. The engineer can now correct the configuration to include encryption, and the pipeline will provision the store this time. Take note that the preventative control is applied before provisioning. And then next we move further up the pipeline, and for the detective and reactive controls, these are enforced post-provision, and they both monitor operating environments continuously. Note that these controls will use the same control definition or rule as the preventative control, but will actively poll the operating environment regularly to check for violations. So here we have the same control requirement that any data store must be encrypted. Our engineer has provisioned an unencrypted data store out of band or out of the usual process. And that provisioning process generated an event message to our operations management system, which detected a violation of the rule and triggers a notification after flagging the data store as non-compliant. At this point, no further action is taken, but the same event message can be passed to a remediation control. Again, the same control definition is used here, but in this case, it triggers a remediation function, which accesses the cloud provider's API and actively changes the configuration of the data store to add encryption. Okay, so in these examples, we've shown a security control, but I want you to understand that these controls can be used not just for security, but any governance and operations purposes as well. Any configuration of a data object can be managed with these controls. So you need to ensure a particular data set doesn't leave its local region. Use a preventative control. You need to ensure that PII data is removed before relocating a data set. Use a reactive or remediation control to trigger a filter process for that to happen. Okay, so back to our DataOps journey here. And the next critical piece to build out on this journey, Epic 3, is your testing capability. If you make a change to a data object or process, how do you know that you didn't break anything? Automated testing can validate changes without time-consuming or manual testing, and this ensures that releases are high quality before entering the operating environments. The idea in DataOps is that every time a data member makes a change, they add a test for that change, the equivalent of a unit test. Over time, the testing harness is added incrementally with the addition of each feature. So testing gradually improves and quality levels also increase. These processes are baked right into your pipelines. These testing harnesses are analogous to the statistical process control that is implemented in a manufacturing operations flow. So tests ensure the integrity of a final output by verifying that work in progress matches the expectations. Testing can be applied to data sets, models, and logic. And for every step in the pipeline, in the data pipeline, there should be at least one test. Start with simple tests and grow over time. And even a simple test will catch an error before it is released out to the users. For example, just making sure that row counts are consistent throughout the process can be a very powerful test. One could easily make a mistake on a join and make a cross product which fails to execute correctly. A simple row count test would quickly catch that and bring it to your developer's attention. Tests aren't limited to errors either. Warnings or informational events can be triggered if data exceeds certain boundaries. So for example, the number of orders in a week may be okay if it is within 75% of its historical average, or if the order levels are above or below that threshold, then that data set could be flagged for investigation prior to being processed. And DataOps is not about being perfect. In fact, the framework acknowledges that the development process is imperfect. Testing ensures they can determine the cause of the issue quickly so they can correct it earlier in the workflow. They can also add new tests to ensure those errors don't happen again, and this will continually improve the quality of the development efforts. So with a suite of tests in place, DataOps allows you to move fast because you can now make changes and quickly rerun the test suite. If the changes pass the test, then the data team member can be confident and release it. The knowledge is built into the system and the process stays under control. Tests catch potential errors and warnings before they are released, so the quality remains high. All right, so let's take a closer look at how you can incorporate testing in a data pipeline. So here we see a set of stages for an ETL testing pipeline. Now, ETL environments can be complicated configurations requiring storage locations, data sets, ETL applications, and the actual job code to be defined. But as we saw earlier, the DataOps framework makes that provisioning process easy by defining all of that in code and making repeated deployments of environment trivial. So with that in mind, the testing pipeline can deploy an entire ETL environment on demand whenever new ETL code needs to be tested. The testing pipeline provisions the environment, then executes a series of tests automatically. In this case, we're testing data quality by checking for correct formatting and reference values. We then test the transform itself by comparing output to expected output. And finally, we test against business rules to ensure that none were invalidated in the transform. The pipeline provides immediate feedback on any errors or warnings from the test to the developers so they can then iterate on the transform code if needed. Or if all the tests pass successfully, the pipeline continues and can deploy the environments to higher level testing stages or on into production. Okay, so on to our final epic of the DataOps journey, building out your pipelines. So in the DataOps framework, there are two categories of pipelines or workflows you will build. The first type is the data pipeline. We'll prepare and condition data for consumption. So here you see raw data entering the pipeline from the left and moves into production processing. Production is generally a series of stages, so access, transforms, models, or streams, and filtering. When data exits the pipeline in the form of refined data, value is created for the business. The data sets in these pipelines are updated on a continuous basis, but process code is kept constant. Now, the worst thing that can happen in this pipeline is that poor quality data enters, but the DataOps framework prevents this by implementing data tests and preventative controls. So this ensures that input data values lay within acceptable quality parameters. Data tests validate the data values of both the inputs and outputs of each processing stage in the pipeline. For example, a zip code should be 5 digits on input, and a complete address should include a zip code on output. These types of tests work continuously to guarantee the integrity of your data, pipelines, and workflows. So quality is built right in and integral to the entire system. If bad data flows through the pipeline, the data tests will flag this and take corrective actions like notifying a team member or even stopping the line before the low quality data impacts higher stage processes. Your data developers and engineers can now focus on innovating the code that extracts value from your data. All right, so let's take a look at some example orchestration pipelines. So here we have 3 different paths of log data generated by an application. On input, tests validate that formatting and values are acceptable before streaming to a new storage location. The pipeline then provisions and executes a data stream for each of these paths, and each of those streams is codified with a set of instructions on processing the data as it moves. Here, our API event logs need some filtering before moving to an alerting mechanism. Our application logs need enrichment by joining to another data source showing IP addresses, for example. And out instance logs need aggregating as there are many instances running for this application. This data pipeline prescribes and then orchestrates each of these paths and the stages of data flow. So next, the other type of DataOps pipeline is the code pipeline. In this type, the data set is now static and new data operations code is executed against those data sets. So the goal of this type of pipeline is to implement new ideas that extract value from data, or this is essentially your computational resource against the data. So here we can see that just like application code, a new idea or feature undergoes development before being deployed to production systems. In fact, these types of pipelines are similar to DevOps-based CI/CD pipelines for applications. They're all designed to facilitate the development of functional code. So key to this is a fast feedback loop so that developers get frequent feedback on errors or issues with their code. So during the development of new features, code changes, but the data is kept constant. Keeping data static prevents changes in data from being attributed to the new code. So remember, your environment provisioning pipeline makes this trivial now and can deploy environments with static data and code versions passed in as parameters. DataOps implements continuous deployment of new ideas by automating the workflow, and it reduces the overall cycle time of turning ideas into innovation. The DataOps framework uses logic tests to validate new code before it's deployed, and logic tests ensure that data matches business assumptions. So for example, a field that identifies a customer should match an existing entry in a customer dimension table. A mismatch should trigger some type of follow-up, and with logic tests in place, the code pipeline can be automated for continuous deployment, simplifying the release of new enhancements and enabling the data team to focus on the next valuable feature. With DataOps, the dev team can deploy without worrying about breaking the production system, and this is a key characteristic of a fulfilled productive team. Okay, now in the last steps of our journey, we combine the data and code pipelines. So in the real world, these pipelines are not separate. The same team is often responsible for both, and the same assets are leveraged. So events in one affect the other, and the two workflows are shown combined here. This joint pipeline captures the interplay between development and production, and between data and code. DataOps breaks down this barrier so that cycle time, quality, and creativity can all be improved. The DataOps enterprise masters the orchestration of data to production and the deployment of new features, both while maintaining impeccable quality. So reduced cycle time enables DataOps engineers to impact the organization in highly visible ways. Improved quality enables the team to move forward with confidence, and DataOps speeds the extraction of value from data and improves the velocity of new development while ensuring the quality of data and code in production systems. All right, so we've completed our journey through the DataOps epic. So what does a successful implementation look like? So DataOps can accelerate the ability of data teams to extract value from data. It requires an agile mindset and must also be supported by an automated platform which incorporates existing tools into a DataOps development pipeline, as we covered today. A well-designed data pipeline can serve as a competitive advantage for data-driven organizations. So here we see how features of the DataOps framework provide valuable benefits to your business. The framework allows higher development throughput, which leads to higher efficiencies and lower cost. The collaborative model of DataOps, coupled with continuous monitoring of operations, provides the capability to scale on demand and builds reliability right into the system. And the test-driven operations model ensures quality from data source to data consumption. And finally, the automation as part of the DataOps framework leads to shorter cycle times and, key to your competitive advantage, faster time to value for your data. All right. So I want to thank everyone for joining us today on the DataOps journey. I hope it was informative for you as well. I want to extend one last invite for everyone. If anyone would like to take a deeper dive into the DataOps framework and see how it would fit in with your organization, we do provide DataOps workshops. And we cover a lot of a deeper look into the DataOps framework and principles, and we can start to discuss how to apply the framework into your organization. And with that, I will pass it back over to Amy to close us out.
Thank you, Rajesh and Dante, for that wealth of information. And thank you, everyone else, for attending today. We hope you can take the lessons learned today and begin your journey to a modern data architecture powered by DataOps. If you're interested in learning more about our DataOps workshop, more information will be provided in our follow-up email along with the on-demand link for the webinar. You can also reach out to sales@stelligent.com for any questions relating to our services and offerings. And of course, you can always reach out to Dante for any questions around DataOps. As we wait for questions to come in, I do want to take this time real quick to remind you that questions can be posted in the Q&A box in the lower right-hand corner. Additionally, please feel free to visit our website at www.stelligent.com for blogs, case studies, and more information around offered services, including DataOps. At this time, Dante and Rajesh, it looks like we have a couple of questions here. Let me see. I'm going to go ahead and read off the first question. It says, by keeping discrete data stored, it may add redundancy. Is this recommended?
So Rajesh, you want to take that one, or?
Sorry, could you please repeat the question?
Yes, absolutely. The question is, by keeping discrete data stored, it may add redundancy. Is this recommended?
It's purely based on your use case. Means if you give the redundancy, so it will provide you a more isolation level for different, making more independent of each other. There's no more dependency there. So sometimes you have to keep certain level of the redundancy to allow you to scale agile independently.
Alrighty, thank you for that. The next question we have is, in the DataOps model, how would you manage schema upgrades where database tables need to be replaced or recreated?
Yeah, so in the DataOps framework, right, all of those schema updates, anything tied to your schema, that's all codified in the sense of a template as well. So managing, what that looks like and defining that, that's pretty trivial, right? And you're just updating a template somewhere and updating the code for that. Where it becomes a bit of a headache, right, is as you start to manage, how do you scale that up, right? So if you're managing just a handful of schemas, it's not a big deal. If you're managing, dozens or hundreds of these, that becomes a problematic as well. So we do have a couple of offerings where we build out sort of a pipeline of a pipeline, if you will, and that enables you to start scaling that process up and growing that as your needs multiply in that area.
Thank you for that. The next question we have is, does DataOps testing happen in one particular environment, or will it be done in multiple environments?
So I'm not a little unsure where you're going with the question, but basically, any environment that you turn up or deploy or provision, and in fact, any step or any change you make to that environment will have tests tied to that, right? So the provisioning of the environment itself will have tests, but then any functional code that I'm executing across that environment will also have tests. So in that point of view, any environment that you turn up would have testing to it. So I guess the answer to that question would be that yes, your multiple environments would all have sets of tests assigned to them.
Great. And the next question is, how do you transition from a monolithic data architecture to a modern data architecture?
Right. So baby steps, right? Typically, we will see an organization try to line up features of their application or particular functions of their application and try to carve those off based on business domains, typically, right? And then you could sort of start chipping away at that monolith application and your monolith data set and pull those out discreetly. Now, the challenge there, and I'll leave it to software engineers to go a little deeper there, is that where do you draw the line inside of your monolithic application, and how do you remove that sort of feature or piece of logic from the monolith without affecting the rest of it, so that you can carve it out. And it's not a simple solution. You know, refactoring an application is certainly a challenging thing, but the DevOps and DataOps framework helps to simplify that a little bit and accelerate the process for you.
Alrighty, these keep coming in, Dante. I'm sorry, we're gonna have to keep you answering. The next question is, can you talk about some of the tooling used in DataOps?
Yeah, so I'll stick to AWS tooling here. Let's see, I think one of these slides. Yeah, so if you think in terms of your two data types of pipelines, right? So across the top, left to right, you have the data pipeline, and in the AWS world, you have AWS Data Pipeline Service, and you have the AWS Step Functions service. So the Data Pipeline Service is a specific service that allows you to build orchestration between the various data services inside of AWS. But it is, I won't say limited in functionality, it just has very defined functionality for the types of orchestration that you can do between sets of data. So outside of that, we have AWS Step Functions. And this is basically limitless, right? Because you can actually write code, functional code that you can call as a step function to manipulate the data, to move the data, to transform it in some manner. So those are the two services we typically see on the data pipeline side. And on the code pipeline side, this is just like any other software CI/CD pipeline, right? So in the AWS world, we're typically using Code Pipeline, which is a managed service CI/CD tool. And then we're using Code Build, which gives you sort of a small containerized environment, typically used for builds, but you can actually extend that into testing and other functionalities as well.
Alrighty, thank you for that. The next question is, the technology seems easy enough. What about the process and people factors? For example, how does your framework facilitate collaboration?
Yeah, so collaboration is key, right? And it's a bit of a double-edged sword, right? So you need the ability to experiment individually, and the framework gives you that capability because you can deploy environments independently. But you've also got all the usual collaboration tools that you see in the software development world, right? So key to that is version controlling, right? So we have this collaborative process inside of your version control that allows you to work together on code without also stepping on each other's toes at the same time. And because everything in the DataOps framework is essentially a code object, you can extend the processes that you use inside of version control into your data processes now as well. So everything you do in the DataOps framework, you're going to write it out as code, and the tooling inside of the version control collaborative tooling there allows you to work together, right? And that extends to your other collaborative tools as well. So if you've got particular agile tools, or you've got tooling that fosters communication between your developers, you can now extend that up to your data team as well.
Alrighty, I hope that answers the collaboration question. Next question is, does data security controls and security testing, can that be an epic in itself?
Yeah, absolutely. So we don't separate it out here because it is tied so much to the environment. So typically when we're in an engagement process, when we build out the provisioning processes for those environments, that's typically where we're also building out all the various controls. Now, we spoke of controls earlier in terms of security, but it's not limited to that, right? So a control can be anything from an infrastructure configuration control to a data set control to a governance control. All of those are even a compliance control, right? So all of those in terms of the framework are all the same, right? It's just a piece of code that sets a boundary or a limit on a particular action, or it sets the rules by which a specific action inside of the pipeline can happen.
Alrighty, and one last question. Yep, I think we have time for one last question,
Yep.
Dante. How can test data be generated in a DataOps pipeline? Where and when in the pipeline should that happen?
Yeah, so the framework itself doesn't specify how you would do that. It would just use existing test generation tooling, right? And there's a myriad of options out there for that. The pipeline itself would just facilitate that and automate that for you. So most of your test generation tooling now will either have an API or a command line usage, and the pipeline either via a step function or just an API call will request that test data for your generation. So that's typically done in the DataOps framework when you are provisioning the new environment, right? So if you think about the two pipelines here inside of your data pipeline, in the middle there, you're conducting your data operations. So that raw data step there is typically right after that, you would create your test data at that stage, and then bring it into the center there, and then conduct your operation against that. There's a few edge cases where you might do inject test data either in multiple stages or even at the end to do comparisons and things like that. But typically it's done in that first phase of the pipeline, the data pipeline.
All righty. I think that is all the questions that we have time for today. So that will conclude the rest of our Q&A. Dante and Rajesh, just again, thank you guys so much for your time today. And thank you and everyone else for attending. A couple of final reminders. Again, the on-demand link and additional information to sign up for the DataOps workshop will be shared afterwards. So feel free to share this with your colleagues as well. With that being said, have a great rest of the week, everyone.